It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 57, where today we have special guest Dr. Jill Tarter here with us. So Dr. Tarter has very, very big in the alien part of physics. I will just say that to all our listeners out there. I know we've had a lot of alien episodes that you guys enjoy, so here is another extraterrestrial episode where so Jill, a little rundown. We have, as a former director of the SETI Institute in America, which is the search for extraterrestrial intelligence, and the co-founder of that institution. So before I, start rambling, Jill, maybe you want to talk a little bit to our audience just about, who you are, what you did, and yeah, just introduce yourself.
Okay, right. Well, I'm formally retired, so my job description would be chief cheerleader for all things SETI. But I got an undergraduate degree in engineering physics from Cornell, a PhD in astrophysics from UC Berkeley. And I got into SETI kind of by accident. So my first year as a graduate student, I was supported to program the first desktop computer we ever had. Now, it took two of us to get it up on the desktop, but once it was there, you could use it, but there was no language. So you had to program the computer in octal. You had to set all the ones and zeros for each of the 11 instructions this computer could do.
Oh my.
And I learned that. I thought it was a lot of fun. And I programmed it to run an optical telescope at an observatory that UC Berkeley had for teaching. And then many, many, many years later, right, I was about to leave graduate school. And this piece of equipment was old and obsolete and surplus. So one of the professors at Berkeley, an X-ray astronomer by the name of Stu Boyer, had been following the workshops that had been conducted at NASA Ames Research Center about looking for life beyond Earth. And he got really excited because they were suggesting using a radio telescope to listen for signals that were engineered as opposed to astrophysical. And he said, UC Berkeley has a radio telescope in Northern California. And so he came to my office because he had no funds. So he'd been scrounging equipment and somebody had given him this old computer and pointed out that I was still here and that I had worked with it. So he came to my office and recruited me to join his project. And I thought, oh, my goodness, I'm here in exactly the right place at the right time with the right set of engineering and astronomy skills, so that maybe I could make a difference in trying to answer this very old human question about, are we alone? And so I started working for Stu on this project, and then went from there to NASA Ames Research as a postdoc and went over to John Billingham, who was running these fledgling discussions about life beyond Earth, and said, I'd like to volunteer for you. And that was it. I mean, I just started doing SETI and I never stopped.
Wow.
That's amazing. And how was this project initially received by the greater scientific community initially? Like, was there kind of a pushback on maybe we should be doing other things or
yeah,
like
there was quite a bit of pushback, and it was sort of people would look at me and say, what's a nice girl like you doing in a science like this? We spent a lot of time in our first years trying to make a distinction between this scientific exploration that we were proposing and conducting and all of the pseudoscience garbage from UFOs and other crazy ideas, right? We had to really stress the fact that this was being done in a rigorous fashion the way you would do any scientific exploration. And the fact that the public and other professionals were willing to have a belief system that was based on stories and wild tales rather than actual evidence was something we struggled with.
Right.
So it's less so today, fortunately. But whenever anybody asks me what I believe about life beyond Earth, I keep trying to tell them that belief is the wrong verb, right? To explore is the correct verb, because if I tell you what I believe, it doesn't change the universe. The universe is as it is, and there is an answer to this question. And we're doing science rather than religion. So we continue to try and stress a scientific exploration.
So during the time that I guess this institution was, like when SETI originally started, was there, I mean, because you were talking about backlash with like, a lot of people, because a lot of the belief system was around, these UFOs. And so how did you, I guess, like, was it like a process, or what was the process of getting people's minds to think, we're not trying to look for these UFOs and these weird things, like we are doing scientific research here? Like, was there a transitionary process, like from the average human thinking SETI is just, it's just looking for, UFOs here and there, to, it's actually looking for alien life scientifically? Like, was there a transition?
No, I mean, it's it's ongoing. The process is always ongoing. And you just have to say to people, well, why do you think that? What evidence do you have? Who's shown you what data? Because if our group ever tells you that we have detected evidence of extraterrestrial technology, you can be absolutely sure that we will provide you with an enormous amount of data to back up that extraordinary claim. So it's ongoing. And for me, the science itself, the science and engineering and technology involved in this search, is so much more interesting than the stories.
Totally second that.
Right.
Yeah.
Right. And I was just wondering, today, like, what is the scientific community in the search for extraterrestrial intelligence doing right now to look for these signals? Are we just using telescopes, looking in the sky and just waiting, or anything specific?
Well, we've kind of transitioned to using the term technosignatures, right? So we are looking, so SETI, Search for Extraterrestrial Intelligence, we can't define intelligence. We certainly don't know how to find it at a distance. What we can possibly do is search for evidence of someone else's technology that's detectable over the vast distances between the stars. And if we find the technology, we are going to infer that at least at some time, there were intelligent technologists that created it. So we are trying to use more broadly this term of techno search to emphasize the fact that it's not just looking for radio signals or optical signals. It's actually looking for any kind of evidence of someone else's technology. So here's an example, and we can't do it now. We can't do it in the next decade, but maybe the decade after that. There is a system called TRAPPIST-1 that we know harbors at least 7 Earth-sized planets orbiting the star. It's a tiny little red star. We've never seen those planets, although you have seen an artist's conception of that system above the fold on the New York Times. A beautiful picture. We don't have telescopes that can image those planets, not yet. We're working on that. But when we do have the ability to make images of those 7 worlds, they're all at different distances from their host star. So they should all be at different temperatures. They should have different characteristics. But when we are able to image them, suppose 2 or 3 or 4 of those 7 turn out to be identical, right? They shouldn't be in terms of Mother Nature, but perhaps someone with a very advanced technology and a lot of energy to commit might have changed many of those planets to make more habitable real estate of the type that they particularly enjoy.
So that would not characterize like an anomaly. That would have to, or that would be more strongly evidence for like someone, you know, actively changing the environment.
Yeah, that's pretty good evidence for geoengineering or astroengineering, we should say. So something like that might be a technosignature. So we're trying to think as broadly as we can about the observable universe and what might be a clue to someone else's technology, even if it's not something that we went directly looking for.
Yeah, that's very fascinating, because when someone thinks of, you know, looking for aliens, they think of, you know, you look in the sky and you're looking for something that's moving, right? You're looking for like something weird. But when you take a step back and you think about, okay, when humans themselves will advance, and, you know, what are we going to do? We're going to go to Mars. We're going to try to terraform different planets, and we're going to try to expand our reaches. And if there are other civilizations elsewhere in the universe, that's also probably what they're going to try to do. And obviously, searching for these signals, as you said, like planets that shouldn't look the same but end up actually looking the same, is much broader of a discovery. I guess broad isn't really the word I'm looking for, but I'm thinking like you see these planets, and it's like a characteristic of the evolution of a civilization. It's not just like some weird occurrence that anyone can claim like, oh, I saw this, but there's no proof behind it, right?
I think, I mean, were you trying to get to the point that proof is a very essential part in all of this? Like, I think that is I think that is the basic, that is the biggest part of this whole thing, because I think, as you mentioned before, previously, this is the biggest question ever asked in humanity's history. Like, are we alone? So it's simply, it's easy to say that yes or no without any evidence, or with lack of evidence, or not enough evidence. But to actually have an answer with evidence is because even saying no is incorrect because we don't have evidence for no. And even saying yes is incorrect because even though it might seem probabilistic, we don't actually have evidence for that. So it's all a very big question about how we can, you know, experimentally find this evidence. And we're going to get into that, but I just realized that like we've been rambling and really getting into the podcast without actually, you know, doing our introductory segments, which we usually do. This is super interesting. It's a super interesting conversation because like who doesn't want to talk about aliens with someone, you know, who is researching aliens. So anyways, but before we actually do get into the podcast, which we already have, let's just start up with our news segment with our comment of the week.
Right. So comment of the week actually comes from Ernest on YouTube here. He says, "Hey guys, I've been listening to your amazing podcast for almost 2 months now, and it has inspired me to keep learning physics, to become an engineer, and to make the world better. I'm now in 11th grade, and I was shocked when I heard that you were born in 2001 because I was born in 2002. That is actually kind of weird because we are in second year, so that's like a 3-year difference. Anyways, he says, anyways, big love from Latvia. So thank you so much,
Latvia.
Ernest. If you want to be, Latvia.
Wow. Nice.
So if you're listening to this podcast right now and you want to be the comment of the week, make sure to leave a comment on YouTube, and you have a chance to get on the
There's
podcast.
a
Also,
sorry for cutting you off, but there's a very big chance, and I do want to
yeah.
mention this, that by the time that this episode drops, we would have 100,000 downloads. So thank you to all of our listeners for continuing to listen and continuing to, subscribe, follow on Spotify. We read those comments. And yeah, so the 100,000 might happen when episode 57 drops. So that's going to be very exciting. So once again, thank you for that. And let's see what happens. Yeah. You were saying
Yeah.
something before I kind of cut you off there?
I don't actually remember. But anyways, if you're listening to this, make sure to follow us on Spotify. Episodes every Monday. And yeah. So I guess to kick off this this podcast once again, I want to bring up this quote that I always think about when I think about looking for alien life, and it's that disregarding, completely disregarding the idea that aliens exist is like taking a teaspoon of the ocean and saying that whales can't exist, right? Because our minds cannot comprehend how big the universe really is. You can say 90 billion light years and everyone will go, okay, that's a big number. But in reality, it's just so difficult to wrap our heads around that. And what we've seen in our universe, what we've actually been able to sort through, is very comparable to that teaspoon of the ocean. And so I guess my question to you, Jill, is how do you think we're going to get over that distance barrier, that vastness barrier, and how we're going to be able to kind of systematically just search through like the bigger part of the universe?
Well, over time. So the first modern SETI paper was in 1959 by Giuseppe Cacconi and Philip Morrison. First SETI observations in 1960 by Frank Drake. And so when SETI turned 50, I did a calculation and I said, well, everybody talks about looking for a needle in a haystack. Let's see how big that haystack is and how much of it we've searched. So there are actually 9 dimensions to that haystack, right? 3 space, 1 time, 2 senses of polarization, modulation, sensitivity. And so I tried to put boundaries on each of those parameters, how much we might have to look in order to be successful. And then I just multiplied them together to get some sort of 9-dimensional volume that my brain doesn't do any good at trying to comprehend or image. And I said, okay, let's set that volume, that total volume that we might need to search to be successful or to draw strong conclusions about the lack of life beyond Earth. And let's just set that volume equal to the volume of all the Earth's oceans. And so how much have we searched? So at age 50, we'd searched 1 12-ounce glass out of the oceans. And that experiment could have been successful. I mean, there are places in the ocean, if you dip that glass in and pick it up, you're going to see little fish inside.
Yeah.
But, 10 years later, when SETI turned 60, that volume was more like a big hot tub or a small swimming pool. And the point is that our ability to search is getting better and more comprehensive exponentially, primarily because the speed of computing is improving. And I look forward very much in the coming years to having multiple observing capabilities around the planet that will allow us to look for transient events, things that only last for a very short period of time. And you have to be looking in the right place at the right time to detect them. So you really need to look at all the sky all the time to do this well. And then the other thing I look forward to is bringing in machine learning and artificial intelligence. So since the beginning, we've been analyzing data that's been collected by telescopes And we've been asking our computers, in this data, are there any patterns that look like this? And those patterns are ones that we have defined as being doable with technology, but not by Mother Nature. They're just the sort of things that you don't see in the astrophysical universe.
So
But,
sorry, were you saying something? I didn't want to cut you off.
well, no, it's just, those are good ideas,
Mm-hmm.
but in fact, there may be other patterns that we haven't thought of. So if we can, in fact, build neural networks that can look at the data a bit more broadly and simply say, not is this pattern there, but is there anything there that isn't noise?
Mm-hmm. So that intelligent of this from SETI is a very important word, because you are in fact looking for intelligent life, not just life on other planets, right? Because all of your simulations, as you stated, that you're comparing your observations to, like what you should be seeing. I'm assuming that now that you just said we're assuming that they have technology, so I'm assuming that assumption entails that the life is intelligent, right? So you're not just looking for life, you're looking for intelligent life.
That's SETI, but there is a whole field, relatively new, called astrobiology, which is in fact looking not for technosignatures, but for biosignatures, looking for the existence of life on other worlds by, for example, looking at the constituents of an atmosphere of a planet. And if you look at the Earth's atmosphere and compare it to the atmospheres of the other bodies in our solar system, you'll see that the Earth's atmosphere is in extreme chemical disequilibrium. We have in the atmosphere at the very same time molecular oxygen and molecular methane. Now in the lab, if you put those two gases together, they instantly turn into water and carbon dioxide. And that's happening in the Earth's atmosphere all the time. But because on the surface of the planet, we have this really strong biological source function, you have oxygen being put into the atmosphere by plants and trees and other photosynthesizers. And then you have methane being pumped into the atmosphere by bovine flatulence, cow fart. Right? And because that is such a strong source, then even though methane and oxygen are reacting in the atmosphere, you still have this chemical disequilibrium signature. So biosignatures. And so the astrobiology community is thinking about how we might build telescopes, spacecraft with sensing capabilities that might allow us to do this chemical analysis of the atmospheres of distant exoplanets and look for this disequilibrium.
Wow. And do you think this will return any information that is, I guess, as you said, it is very different because you're using astrobiology versus, observational evidence from telescopes here. But I guess the question would be like, when you're comparing these two, looking for intelligent life versus looking for life, I guess you already said belief doesn't matter, but I guess this is a question. Like, what do you believe would be more beneficial? Like, would knowing if life exists, like if, let's say, a unicellular organism exists in some planet, like would that really be beneficial to us? Like, what is your opinion on that whole situation versus intelligent versus versus searching for non-intelligent?
I actually think finding life somewhere else in our solar system and showing that it was indeed a second genesis and not just life that got swapped between the planets over time, either from here to there or there to here, I think would be extraordinary, because in physics, there's a way of counting, right? It's 1 to infinity. Whenever you have a singular example of a phenomenon, it could be that that is unique. But whenever you find a second example, that number 2 is really important, and you're going to know that whatever it is ubiquitous. So if we were to find a different example of life of any kind within our solar system, and it really was an independent genesis, then we know that life is going to be ubiquitous, right? It's going to be
Yeah,
everywhere.
that would be absolutely incredible
Yeah.
if we find a second genesis of life in our solar system that is so incredibly local that, you know, that's really a telltale sign that it could actually be absolutely everywhere in the universe.
Sure. So keep your eyes on the Europa
Mm-hmm. Everyone's looking at that one right now. Yeah.
flying through the plumes of the uh, volcanic outputs from under the icy crust, seeing if you can see some evidence of biology or biogenic precursor molecules in those plumes.
I believe Europa was the first one where they discovered, or at least I believe I was hearing for the first time Europa was the one where, oh, its icy surface might have water or some sort of, earth-like element underneath that might allude to life on Europa. I know it was like a very big deal, and I think it still is. A lot of people are still exploring it for a lot of these reasons. But
It's
who
taken
knows?
a lot of different observations to convince ourselves that underneath the ice there is really a liquid, salty ocean. And then when we discovered these plumes from cryovolcanoes coming out of the South Pole, it was really exciting. And so, yeah, I mean, people are taking bets. Some people like Europa, some people like Enceladus, some people like Titan.
Mars? What about Mars? No one likes Mars. Just
Well,
nuking the ice caps is not a possibility.
well, if you're talking about extant life as opposed to extinct life, then it's going to be kind of hard for Mars, right, to have extant life unless it is in liquid reservoirs beneath the surface. And so, yeah, we're planning on that too. We're planning on trying to look for that. And in fact, these recurrent slope linei, these areas on the sides of valleys that wet and dry, depending on the sunlight, are really of interest. And as we are sending rovers to Mars, we're now having to think about, we thought, oh, well, we'll sterilize the rovers as best we can. And it's unlikely that any biological material that we bring on these rovers to the surface of Mars will survive. But now we're having to define areas which are forbidden, which you're not allowed to think about putting a rover in because of this water or liquid that shows up on the surface, which might in fact be able to host and to grow life that we bring there. So, Mars is a really special case. If we find evidence of biology, we're going to have to make very sure that it isn't us. So, we could well be Martians. We have meteorites in our labs that are pieces of Mars that have been chipped off by an impact and floated in interplanetary space and eventually landed up on the Earth. In particular, the place where we go looking for them is the Antarctic ice flows. And when the spring comes around and you get these meltwater pools, you go looking for this white background and these little black rocks, right? They're pretty easy to find. And we've had it with a rock called Allen Hills 84001, that there were features in that meteorite that were best explained by being alive, or at one point alive, that these were microfossils of life. And the community went into overdrive debating whether this really was evidence of biology or whether it was evidence of some sort of geology. And in the end, two things happened. One is that we developed a whole suite of new instruments for studying micrograms of material that we had never had before. So that was a really good driver for technology development. And the second is over time, although the authors of that paper still contend that it's best explained by biology. Most of the community has come up with other ways that are abiogenic, that don't require life, to explain what we've seen. But we're back at it again now over the last few months. There's been a claim that phosphine molecules have been discovered in the clouds of Venus. And more than that, the claim is that there is no known way to produce those large amounts of phosphine that are being claimed that doesn't require intermediate step and modification by biology. So when we find phosphine gas on Earth, it's always associated with biology. So we're back at it. Are we really clever enough to rule out all potential chemical pathways to producing phosphine in the clouds of Venus? Right? Can we be absolutely sure that we're so right that we can make this astonishing claim that you can't have phosphine there if it's not biology? We'll see. We'll see how this plays out.
And quick question, how do we know for sure that these like sediments in the Antarctic in Antarctica are like all from Mars, or aren't like a mix from like Martian rocks and Earth rocks together?
Okay, so the meteorites that we claim are from Mars, we say that because of the gases that are trapped in the meteorite, and they represent they're pretty distinctive of the atmosphere on Mars. So that's how we claim that we know that they're from Mars.
Okay.
And so all of these things with Mars especially, what do you feel about Elon? I mean, you've definitely heard about the Elon Musk SpaceX, going to Mars and everything, colonizing Mars. So I guess with all of these other options also available to us, as you very well mentioned, in the solar system itself, obviously Venus is an exception in itself, but like Europa, for example, like basically the question here is, do you believe Mars is the correct planet to target in our solar system?
Well, certainly it's the closest, right?
True. True.
Europa's a lot farther away, and Celadon's even farther. So this is one of the reasons the advent of privatized space exploration is one of the reasons that we're getting so agitated and excited about questions of what's okay to do on Mars. When it was space agencies, then COSPAR, which is an international committee on space exploration, could set up a set of standards about how you have to sterilize any body, and the standards varied on the basis of how likely you thought it was that life brought to another body could thrive. And so the space agencies have been self-regulating. They've been pretty good at complying with the COSPAR guidelines. Now you're beginning to talk about private enterprise. And there's no way to enforce these ideas about what's good and what you shouldn't do. I mean, there's no body. COSPAR is an offshoot of the UN, but still, we're not sending UN peacekeeping troops to SpaceX in Southern California to say, "Thou shalt not." So we're into another era of how we decide what's appropriate, what's inappropriate, what's the best for humanity. So there's actually, under the International Institute of Space Law, there's a subspecialty called meta law. Been around since the 50s, I think. And here people are trying to understand what the legal and ethical principles are for dealing with the other, right? So, right, how do you formulate a golden rule for interactions with an entity that isn't human? How do you know what they would like to have done unto them, right? How do you deal with this? And so there's a question, at least in the scientific community, about if we find evidence of extant life on Mars, should we leave Mars to the Martians, right? What are their rights? How should we deal with it?
I was a little surprised when I heard the term international space law. Like, that's a thing? Like, there's no way that's a thing.
It is. It's not very well established or developed. It's actually taking off from the law of the sea. That's the basis for trying to formulate these legal, ethical principles.
Yeah, because you can't own any part of space, right? Like that. I mean, so legally speaking, I guess like it's so like there shouldn't be a problem with simply, you know, going. Oh, actually, this actually kind of makes me think of a question, because Parker and I were talking about this in a previous episode, and I thought about it, but I'm not 100% sure. If, let's say, like I build a rocket and I'm trying to like send it into space, would I need like some legal documents from the country that I'm sending it from or something like that? Like, what's the situation with sending a rocket or anything really into space? Like, is there a legal like a boundary for space as well? Like, would you know this?
Yes, there is. You have to get a launch. You have to get a launch permit from a body that's based in the UN.
Oh, okay. Oh, and, wow, that's pretty high up. Okay.
You know, we're facing a tragedy of the commons with respect to at least low Earth orbit, which is that we have so many pieces of stuff up there that we're either approaching or have exceeded something that's called a Kessler limit, which is that even if we never launched another spacecraft, the density of stuff up there now is already so high that they will collide with one another and break up into zillions of pieces that will collide more frequently. And so, you know, it's possible that at least in sun-synchronous low Earth orbit, we could lose access to space for a century or so until all this stuff collides and turns itself into dust eventually.
That's a long time.
Yeah. So it's generally referred to as space situational awareness, trying to track all this stuff and understand what collisions might happen, and to the extent that there is propulsion on board any of these objects, move it out of the way and avoid collisions. And now it's required that when you launch something, you have an end-of-life strategy that is enough fuel to boost it up out of the low Earth orbit into a graveyard orbit where it will be safe for a very long time. So we didn't worry about it at first, and we've gotten ourselves into this potential tragedy of the commons.
Because there's a lot of dust and debris as well, right, in space that we weren't exactly, as you said, like thinking about when we were originally launching our satellites. But now I'm assuming, obviously, that debris actually is starting to add up and might actually play quite a devastating role, a destructive even, if it goes south. But, that's a possibility that I guess we didn't think
if you
about.
look at the windows of the space shuttle, for example, you can see these pits that have happened, that have been caused by being hit by dust grains and things like that. It isn't, though, until you get to thinking about interstellar travel at speeds that are some fraction of the speed of light, that these dust grains become incredibly potentially harmful, because the kinetic energy, when you're moving at those speeds, the kinetic energy involved in a collision with even a small dust grain, it's, it's like a freight train coming at you.
Yeah.
Can imagine.
All right. So, really quickly, before we get into our next question here, we just wanted to let everybody know that is listening right now that, we're aware that not everybody is in university, like Ray and I, and but are still interested in these topics of science and physics and all that stuff. And we truly recommend brilliant.org, where they have courses on, math, astronomy, but is particularly relevant in this episode, where you can go and learn about all these interesting topics on observational astronomy and all these interesting topics that Ray and I are actually learning right now in school. Now, of course, all of these courses are interactive. You can learn and test your knowledge all at once, which is, of course, the best way to learn. You can't just watch YouTube videos and then expect to retain everything. And so brilliant.org also has these daily challenges, which are always fascinating, creative, and they really test your critical thinking skills. And so we really recommend
They
that.
also have a really cool data collection course, I believe, like where you learn almost how to collect data, like experimentally collect data, with, especially when we're talking about any type of observational astronomy, like all of that would play into this situation. So for the first 200 listeners who click on that link, get 20% off your premium membership. So you click that link in the description below, or you can just go to brilliant.org/MPP. And you get 20% off your premium membership, which I think is a pretty sweet deal. So click the description, link in the description below. So
Awesome.
Segueing back on, I kind of wanted to now take the conversation back to when Jill didn't know astrophysics. So before everything started. So we usually have like this segment on whenever we have a guest on the podcast, where I call it the classic question, where it's almost like, because it's so classic to our podcast, where I basically ask them, well, what got you into your field? So I guess, Jill, what got you into, I guess, liking aliens and like astronomy, physics? Like, what was the whole situation?
So my dad was a professional football player very long ago, for a couple of years. And my mom was an executive in retail. So if you look at pictures of me when I was a little girl, I'll be dressed up in these pinafores that are gorgeously ironed and starched, and I have little lacy socks and Mary Janes on my feet. And I'll be holding a big old fish, right, that my father had caught. And so I had this tension between spending all my time with my dad and being a tomboy, and then my mom getting fed up with this after a while and saying to my dad, Jill has to spend more time with me and do girl things. So my father had this conversation with me when I was 8, 9, something like that. And he said, your mom thinks that you need to spend more time with her doing girl things. And I just couldn't have been more angry. It seemed to me so unreasonable that you had to choose to do one or the other. Why couldn't you do it all? And so, tears, because I even at 8 and 9, I knew that if you wanted your father on your side, tears helped. And so we continued this conversation. And after a while, my dad said, well, I guess if you're willing to work hard enough, you can do whatever you want. And I said, I'm going to be an engineer.
Wow.
I don't think I really knew what engineers did, but I knew my dad had a lot of friends who were engineers, and they seemed to have a good life. And then a couple of years later, my dad died, right? So I learned this really difficult carpe diem lesson about, don't put off asking a question today because you might not have the person around that can answer it tomorrow. And so I just was left with this really stubborn, well, I told my dad I was going to be an engineer, so damn it, I'm going to be an engineer. And I went to engineering school at Cornell. I was the only woman in a class of 300 entering that year. That was a bit of a real drag, but again, stubborn. I told my dad I was going to do it. And then I realized that I was getting very good problem solving skills in this engineering course. But at the end, and it was a 5-year course, at the end of it, I looked around and I said, engineers are as boring as my professors. I'm going to find something else to use my problem solving skills on. Yeah, it was a fair criticism of engineering school back in those old days. And so I stayed around Cornell and just started to take a whole bunch of different graduate courses in all kinds of different fields, and ended up taking a course in star formation that was taught by Edwin Salpeter. He's fantastic teacher. And who knew that stars had a life, right? They were born, they lived, they died in different ways. And I just thought, oh, these are interesting problems. And so I decided to go into astronomy as a graduate student. And then, as I've already discussed, SETI came along, not because that's what I was set out to do, but because I knew how to program that old obsolete computer, that someone came and asked me to join their team. And I thought, yeah, I got hooked, and I've stayed hooked.
Wow.
So you were taking all of these graduate courses and you stumbled upon astronomy. Were you interested in a specific topic in astronomy or just astronomy in general?
No, it was the star formation that got me interested. And then, I started to, I didn't do much astronomy as an undergraduate engineering student, so I'll go back and study the theoretical foundations and yeah.
Being the only woman in, as you said, 300 students? Like, I was reading that on your Wikipedia page, and I'm like, that like, I mean, I guess, like, what, I can't even find the words. What was your experience like as being the only woman in that program?
Well, it wasn't great. Again, old long ago times and mores. So not only was I the only woman, but because I was a freshman woman, I was actually locked into my dorms at night at 10 o'clock, and the doors didn't open again till 6 in the morning. And so I missed out on the team building piece of the engineering education because all of my male students, nobody cared when they went to bed and whatever. So they're all over on their quad forming teams to answer all the problem sets that you have to do as an engineer. You take the odd numbers, I'll take the even numbers, we'll compare, et cetera. And so there was this whole business of learning how to be part of a team that I never got. And that really was a problem later on. I was never part of a team until I had to lead a team. And if you don't know how to get the best out of the individuals and their unique skills, it's really hard. So that was a lesson I had to teach myself much later in life, which would have come naturally had I been one of the guys in my engineering cadre. And, there were all kinds of embarrassing and difficult things it's better today. You know,
Yeah,
2
for
years
sure.
ago, I did some work with Cornell, and 2 years ago, at least, the entering engineering school was 51% women.
Wow,
So
that's incredible.
Wow, that's amazing. That's a
Wow.
big percentage increase from the 1 in 300
Well,
to 51.
it's a majority.
it's also a lot of years, guys.
Yeah, of course, of course,
Yeah.
of course. That's a big factor to play into it.
Wait, that's incredible. So were you, yeah, I'm guessing you were the only woman throughout your entire 5-year course because
No, subsequent years, some other women entered the engineering school.
right, but not at your level, right?
Wow, that must be, yeah. Because I was also thinking about the one thing you said where they used to lock your doors at 10 and like what? How is that even legal? Like they just lock the girls' doors at 10 p.m.? Like how can they do that? Like
It was called a policy in loco parentis, right? So you take these fragile freshman females and you have to act as if you were their parent and protect them.
wow.
I mean, I just remember. So I had a policy that I set for myself, which is I didn't date any engineers. I just didn't like the fact that they showed up for dates with a slide rule on their belt. So I made it a policy to date architects. There was this tension between engineers and architects on the campus. And so the architects every 3 years had this amazing gala ball, bacchanal, right? They take some building that was going to be demolished or redone, and they go in and they decorate the hell out of it. They create an atmosphere, they create a world, and then have a big party. So as a freshman female, I had to get permission, right, to go to this ball, and in particular, permission to come back to the dorm after 10 o'clock, because the thing didn't end until 2 in the morning. And so it was great fun. I went. Actually, my partner and I won the dancing contest.
Wow.
The theme that year was Black Orpheus. So Rio, Brazil, the samba, etc. So that was such a big deal.
Wow. You have to get a permission slip just to come to your own dorm? That's
that sounds insane.
I mean, that was literally a different world that we lived in at that time.
Yeah, it was. It's gotten better.
For sure.
And worse. Now we discriminate against other categories and classes in a way that we shouldn't.
Mm-hmm. Yeah, the situation right now with race is becoming more of a question and less sexuality, which was the case. But I believe it was it this year or last year, I believe, where 2 women scientists for the very first time ever individually won a Nobel Prize without the inclusion of a male anywhere in their thesis, right? Mm-hmm. So I'm assuming like that was a huge moment for women in science. So like it's definitely improving. Like we definitely see that curve like moving in the positive direction. It's not there yet, but it's still in the positive direction, which is good.
Mm-hmm. Yeah, but in this country, when the discrimination and disequilibrium has guns in the mixture, it's we're really at a very difficult social time right now.
Yeah. Oh, yeah. Wait, you're in America, right? Oh, yeah, you're in America as well. By the way, I don't even know if we mentioned. Oh, yeah, University of Toronto. We're in Canada, so we're a little different mindset with the whole gun situation. Anyways, let's not get into Second Amendment. let's stick to math and physics.
Yeah. So I wanted to ask you, in like before actually going to college, in high school, were you set on becoming an engineer just because you had told your father, I'm going to be an engineer? And did you actually enjoy the physics, the math, and all the requirements to becoming an engineer, so that also motivated you to go into it? Or were you just doing it because that's what you put your mind to?
Well, that's what I had decided I was going to do. And so I had problems with guidance counselors. who said, "What do you want to take calculus for? You're just going to grow up and have babies, right?" That
Wow, that is
negative counsel.
terrible to say. That is a
Terrible.
terrible.
But on the other hand, I had a physics professor called Doc, right, who became a surrogate father for me. He was wonderful. And I don't, okay, this is really crazy. But at the time, if you were a high school girl, what you do is wear a chicken wishbone on a gold chain around your neck. I can't defend it, but that's what you did. So I went to Doc and I said, "Doc, I want to silver plate this thing, right? I want my wishbone to be special." And so he worked with me after school. We wrote to all kinds of companies that electroplated baby shoes and all of that sort of thing to find out how you could do this. And I just loved working with him. And eventually we managed. And of course, you couldn't do it today because silver arsenic is not something you allow high school students to play with. But we did it, and I finally got a silver plated wishbone, which tarnished within a day. But I used it for a while. And so I really enjoyed the ability to work on a far out crazy idea with someone who is so supportive.
Wow, yeah, that must have really been nice. I mean, that experience. So continuing on to your whole PhD experience at Berkeley, your master's and PhD in your doctoral experience. I was reading that in your PhD thesis, the term brown dwarf was coined for the very first time. So maybe, and I read that and I'm like, you know what? I'm not gonna read, because usually what I do is I look at the dissertation, look at the thesis report, maybe like understand what they're talking. But the moment I read brown dwarf, I'm like, you know what? I'm just gonna let her do the explaining. This is too interesting. So maybe you would want to talk about your topic for your PhD thesis and how did brown dwarf, become, I guess, so important.
Okay, so graduate school was better than undergraduate school, but it wasn't
Fantastic.
perfect.
Okay.
My first week in graduate school, there were 2 other women who entered in my class, and the 3 of us were called to the department chair's office, and he welcomed us by saying, "You women are so lucky that all the smart men got drafted for Vietnam."
Wow.
Right. And then so
Wow.
we didn't say a word. I mean, we were so stunned. We got outside after this was all over. We went out in the hall. We said, "Holy, did he really say that?" It was amazing. So brown dwarfs, at the time, we were dealing with what we called in astronomy the missing mass problem. Eventually, it would turn into dark matter, but back then we called it the missing mass problem. And when you looked at the orbits of stars towards the edge of the Milky Way galaxy, they were moving in a way that implied that there was more mass interior to their orbits than we could measure by looking up the amount of stars and gas and dust. We summed that all up and we came up about what we thought at the time was about 10% short. Okay, so what can be supplying that mass? And my thesis advisor wondered if it might be little stars that never turned on, because the physics of what determines what mass is a cloud of gas is going to break up into is different than the physics that defines what masses of stars are going to be able to stably fuse hydrogen to helium at their cores. So you could form stars that were too small to be able to do this stable fusion. They might fuse a little deuterium, but they would essentially just continue to contract and go dark. So might there be a lot of these things out there that were contributing to mass that we couldn't see? And so I wanted to model them, right? So you need an equation of state to define the interior of the star. And so I used actually nuclear codes from Lawrence Livermore to make that model. And that wasn't unique. Other people had done that before. But then if you want to figure out what these stars look like, at what wavelengths there is a peak of emission from the interior of the star, you have to fit an atmosphere around that interior model. And at the time, at low temperatures and densities, the opacity tables that we had access to were terrible. And I never managed to successfully get a stable atmosphere around my interior model. So I couldn't tell astronomers, well, if you're looking for these, you should be looking at this wavelength or that wavelength. It was really frustrating. And so I basically couldn't define a color temperature for these stars. And having a friend who worked with Edmund Land at Polaroid, she told me, well, Edmund Land said that brown is not a color. I said, well, that's what we need. We need brown dwarfs, right? Because it's not a color. It isn't giving anybody the wrong impression of what part of the spectrum you should look at to find these things. And so that's what I called them. It caught on, and it took actually 25 years before the first one was ever observed. So they are real. Was a good idea.
Are these brown dwarfs, like, they still have like a hot core, right? They're still fusing like
no, it's
heavy?
cooling down. All right.
Okay.
It got hot when they collapsed, right? And the rate of nuclear fusion is a very strong function of the temperature. They got hot, but never hot enough to keep this up. And so the rest of the process is just cooling off and crystallizing the interior.
And
Okay.
does the knowledge of brown dwarfs, and I'm assuming again because your SETI opportunity simply came by and it wasn't something planned, so I'm gonna take the assumption that your thesis wasn't really based anything to do with extraterrestrials or something like that. It was just purely based on the astronomy and physics behind your stellar systems, what you were studying at that time.
That's right. And I did a postdoc at NASA Ames Research Center.
Yeah.
And the idea for the postdoc was that NASA was thinking about launching what they called at the time the shuttle infrared telescope. And so I went to work with those folks to figure out, okay, where should we look for these things? How do we build the instrumentation to do that? And the shuttle facility eventually then became SIRTIF, the Space Infrared Telescope. And so that's what got me to NASA Ames, was how NASA could build an instrument that would find these things if they were there, if they were real. And they are, and they're quite significant in terms of their number. But once I was at NASA Ames, then I was right next to John Billingham, and I think he called it the Interstellar Communication Committee or something. So I just raised my hand and volunteered.
Wow, that was
So do we find brown dwarf systems kind of like a solar system where you have like a brown dwarf and then like orbiting bodies, or have we seen brown dwarf like in binary systems with a regular star, or two brown dwarfs orbiting each other, anything like that?
I'm not, I haven't followed it. I'm not sure that we found two brown dwarfs orbiting one another, but we certainly have found brown dwarfs in binary systems, right? And so it's really hard to decide whether what you're seeing is a massive Jupiter or actually a brown dwarf. And the distinction is something you can't see by observation. It's whether or not it condensed independently or condensed in orbit around another star. So,
So when actually observing these systems, right? I was reading on this AI bot made by Google, right? Like the Google AI, where they specialize in finding exoplanets. using, I believe, transitionary processes, right? Like measuring brightnesses of the parent star and determining whether or not a planet that would have passed it is in the hypothetical Goldilocks zone.
Right.
So I guess the question here is, does that just like remove the job of any human scientist working at SETI? Because isn't that basically doing the work that you would have to do with your telescope?
Well, this idea of exoplanets, when I started at NASA Ames, we didn't know of any planets around any other stars. And so because SETI was interested in this question, and if planets were very rare, SETI wasn't going to have much chance of being successful. So we started holding workshops on how you might detect planets around other stars.
Wow.
And for example, Bill Barucki, who was the PI for the Kepler spacecraft mission, which was so productive, he attended those workshops. And he's another stubborn guy, right? He came up with this mission and submitted it, I think, 7 or 8 times before it was finally selected for flight. So yeah, the transit method is one. There's another method called the radial velocity. So transit works well if you're if the plane of the planetary orbit is in your line of sight, because it'll pass in front of the star.
Mm-hmm.
Radial velocity is a measurement of absorption lines in the stellar spectrum. And if the planet is orbiting in such a way that sometimes it's behind the star and it's pulling the star away from you just a little bit, and then when it's in front of the star, it's pulling the star towards you, then when you look at the emission spectra from the star itself, you'll see that the emission lines are red shifted and blue shifted periodically, red shifted.
Mm-hmm.
So that was another method that was developed in these workshops.
And was this method proposed because we saw this effect with the sun and Jupiter, how like the center of mass between the two is slightly off the axis of the sun, and so we see it wobble. Yeah.
Mm-hmm. It's that planetary wobble, right? That I'm assuming caused people to assume this radial velocity method would work, right? And
stars are moving randomly around us in the galaxy, in the local center of rest, and their motions are on the order of 100 kilometers per second. So you need to pick out this radial velocity change, which is on the order of 10 kilometers per second. And now we're pushing it down with better spectrometers to 1 kilometer a second. So it's a very dicey measurement to make.
Interestingly enough, I feel like I should mention this. In our astronomy course, we actually made that calculation using the radial velocities. We were like given a data set and we were supposed to like estimate that I think we were basically just supposed to analyze the system, but I understand what you're saying by estimating the radial velocities to understand the relationship between the planetary body and the star, because it could really tell you a lot of information about it.
Right, and it gets harder. System. It gets harder when there are multiple planets, because then you're stuck.
I can imagine. Yeah, because then would you not also have to factor in like planets influencing each other, and not only by the star? Like, I'm assuming you also factor that in, right?
Yes.
Yeah. So that would be an important thing to take into consideration, I'm assuming, when we're looking at that.
Are there any other ways to detect exoplanets, or is that pretty much it?
Yes. Gravitational lensing is another way, right? So if you're looking at a distant star and another star passes in front of that, the gravity from that star can cause the image of the distant star to split into multiple images, right? And if indeed, and so you'll get you'll get the intensity of the distant star also changes. So you'll, as this passage happens, you'll get the brightness of the distant star to increase and then decrease. And that's kind of usually weeks sort of time scale. But if the star in the foreground also has a planet orbiting it, then on top of this rise and fall of the intensity of the distant star, you'll have a little bump, right? That's caused by the fact that there's also a planet. And when it transits or passes in front of the star, you get a small additional gravitational lensing from that planet.
And I'm assuming, again, with multiple planets, this would become even more difficult, right?
Yeah, well, there is no, there is no unique solution to the caustic curve for even one planet, but you can get, by simulating a whole bunch of things, you can get a good, this is most likely what it is.
Mm-hmm. I had maybe one of our last questions here.
Yeah, we're getting close on time.
Yeah. Just this could be maybe just like a brief answer, but do you think that the future of astronomy and astrophysics really does lie in finding like concrete definitions for dark matter and what it really is?
Yeah, I think our challenges are, okay, what the heck is dark matter? What the heck is dark energy? And as you go back in time to higher densities and higher temperatures, at the moment, we can't make gravity and quantum mechanics play nice together. So that is a problem that lots and lots of people are working on. Yeah. And I mean, it's amazing that we have pieced together this scientific, what do I want to call it? Creation myth based on observing just 4% of the matter energy density in the cosmos. And we know that it will change in the future. It will get modified as we learn more. But I think it's astonishing that we've been able to do as well as we have, given the limited amount of energy and matter that we have access to.
Right, because there is a shift in our perspective when we realize, like, hey, there's a lot of things we just can't see at all. What do we do now? Right? So then we have to start thinking about, okay, like how do we find this invisible stuff? And,
it's a big part of our universe.
Yeah.
Yeah.
Sure.
So that's taken into consideration.
So your measurement techniques have to be on very large scales. You don't sense this stuff unless you're looking at things that are extremely large.
So maybe for the closing question, I can ask you, this is obviously very, very subjective, but when you retired in 2012, I believe, this is like, imagine I'm like a science auditor almost, like coming and I'm asking you, or like SETI, just the institution of SETI, not you specifically, but since you were the director, I'm assuming you would have a lot to say against this question. So if, let's say, I'm asking SETI in like the last 30 years, 40 years of it running, what have you come up with? Like, what can you tell me that I didn't know 50, 60 years ago? Like, without SETI, what do I know now? Like, with SETI, then I wouldn't have, basically.
Sure. Well, I mean, the game changers over that time period have been two. They've been extremophiles, organisms that we find on this planet that live in conditions which I was told as a student could not possibly host life, and exoplanets. And those two game changers have now made it the next question you ask is, given all this potentially habitable real estate, is any of it inhabited? Right? Either by technological civilizations or by some other biology. And that's what we know now that we didn't know before. So this idea of life beyond Earth is really something whose time has come. So in 2020, 2005, I think it was, Craig Venter, sequenced the human genome. But he also made the following prediction. He said that the 20th century was the century of physics with all kinds of success of special and general relativity and quantum mechanics and all that sort of thing. And he said the 21st century is going to be the century of biology. And that was bold, and I think that was right, but I don't think he was bold enough, because I actually think the 21st century is going to be the century of biology on Earth and beyond. And, so again, going back to Craig, I used to say that we would never be able to understand, with respect to biology, what was necessary and what was contingent. I mean, it just happened that way here. But actually, I think synthetic biology is now allowing us to not need a second example from somewhere else to puzzle this out. I think maybe we can do it in the lab. And I think that, I think in some sense, the question of, is there life beyond Earth is driving a lot of this new techniques.
Yeah, that is, I think, the fundamental question that all of us are striving for, right? Like we always, because we want to know if we are all there is to the universe, which doesn't seem likely. But again, we need that evidence, right, that we were talking about, that formidable evidence. So, yeah.
Yeah. So, Jill, thank you so much for coming on to the podcast. This was obviously, for us, an amazing opportunity. We learned a lot today. And, we also have tons of other questions now. And so, later down the line, maybe you can come on for another episode. That would be awesome.
Okay.
And,
well, thanks for inviting me, but I do actually have to run off now.
Yeah. So once again, so again, we're just gonna make the end real quick. Thank you so much for coming on. So again, as Parker said, hopefully we'll do this again. Parker, you just want to wrap up with where you guys can follow us real quick.
Yeah. So follow us on Spotify, Apple, subscribe to us on YouTube, and follow us on Instagram at math.physics.podcast. And so, yeah.
Stay tuned for the next YouTube video, because it's going to be our 100K Q&A that a lot of people have been asking for. So it's only going to be on YouTube, not anywhere else. So just be sure to check it out if you guys are interested. So once again, Jill, thank you so much for coming on.
This has been episode number 57 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.